G'day guys, we've got an economics problem today, specifically an optimization problem, where we're going to be looking for the Hicksian demand functions for two goods of this agent, which has a utility that is expressed by this function here. Now, Hicksian demand asks us to minimize expenditure given a particular utility set. So basically it's saying, if I want to get this much utility, what's the cheapest way that I can get there? So that's what the Hicksian sort of optimization problem looks like, rather than having a Marshallian one, which says we have this much money, we have this budget, how much utility can we get? Hicksian, we look at the fixed utility and we try and minimize the cost to get there. So let's get started. So it says here, set up the utility minimization problem for this sort of Hicksian demand. So what we're going to try and do is, so let's have a look, part A. We're looking to minimize the agent's expenditure. So expenditure function is just the price of good one times the number of good one that you buy plus the price of good two plus the number of good two that you buy. So let's just call this the expenditure. We'll just call it capital letter E, is the price of good one times the amount of good one that you buy, add to the price of good two, add to the amount of good two that you buy. Cool. Now, this is subject to, so our boundary or our condition on this is that we have a fixed utility which is given by x1, x2 squared. Cool. So basically we're asked to minimize the amount we spend given a fixed utility which is given by the consumption of the goods in this manner here. So that is part A. Wasn't very complicated, but the question will complicate itself up very, very quickly. So no need to worry. We have part B. Derive the agent's Hicksian demand. Okay, so we're going to use the method of Lagrange in this problem where we take our objective function and we minus the constraint multiplied by a Lagrangian multiplier. So basically what I mean by that is we're going to input these into our Lagrangian expression. So L is equal to P1 x1 plus P2 x2 plus the multiplier times, now we make this one here equal to 0, so we just take everything over the other side. So we have U, the utility, minus x1 x2 squared, and that is our Lagrange formula. So basically from here, if we're going to minimize this function with this constraint, what we're looking to do is we're looking to get our what they call first order conditions, which means the derivative with respect to the prices and the Lagrangian multiplier have to all equal 0. So let's just write that down, our first order conditions. So what we're going to do is we're going to differentiate this function with respect to x1, x2, and lambda. So we're going to have dl dx1, and that's equal to, we're going to have price 1, and that's going to be minus lambda x2 squared, and that has to be equal to 0 because we're looking for a saddle point here. So we also have the derivative of the Lagrange with respect to x2, which, like x1, you start with your P2 minus, and in this case, because we're differentiating with respect to x2, this is just a constant, that'll come down. We have 2 lambda x1 x2. and that's equal to 0. Our third and final first order condition is that if we have dl d lambda is equal to simply u minus x1 x2 squared, also equals 0. Great. So what we're going to do from here is we're going to use these two first order conditions to eliminate lambda by, let me just move this. Cool. Now what we're going to do is we're going to put them both in terms of price 1 and price 2. So we're going to have price 1, we'll take the lambda x2 squared over the other side. And we've also got P2 is equal to 2 lambda x1, x2. Now what we can do to eliminate the lambdas, and so I don't have to do any more working out, what we can do is we can put one over the other. So we can say P1, and we can do that, over P2. I'm just going to get rid of these equal signs and just put 1 equal sign there. And the lambdas cancel each other out, which is nice. So from there, we have P1 over P2 equals x2 squared over 2x1 x2. But what we're going to do, obviously, we're going to simplify this. The x2 will cancel with the squared at the top, and we'll be simply left with x2 over 2x1. Great. So what we can do now is we're going to basically make these in terms of x1 and x2. So I can make it in terms of x1 by going, well, just moving the x1 to the top. I can say, well, x1 is equal to P2 x2, so I'm just moving that up to there, moving that up, and divided by P1, and x2, it's probably a lot easier to see, is equal to 2P1 x1 divided by P2. Sorry, I just had to check my math. Great. So now what we're going to do is we are going to substitute both of these. To get our Hicksian demands, we have to substitute these into our utility function. So we have to get a function that is just in terms of a fixed utility and the price. So what we're going to do is, to start with, let's go about entering in x1. So I'll change color. We've got u is equal to x1 x2 squared. We're going to enter in x1, which is our sort of optimal demand. And this is another optimal demand. So we'll enter our x1 in, and we're left with P2 x2 on 2P1 times x2 squared, which is equal to P2 x2 cubed divided by 2P1. Okay, So once we've got to there, we then have to get the x2 to the power of 3 by itself. And so we're going to, and remember it's just this u equals this. So we're going to go x2 is equal to 2p1 u over p2, and this is all to the power of 1/3, or it's the cube root. Cool, and we can also do exactly the same for x1. We can substitute x2 into this function, and we're left with u is equal to, rather than writing, well, we're going to have x1, but rather than writing x2, we're going to go 2p1 x1 divided by p2, and we're going to square that. So from there, what we get is we can then rearrange that. So we can make it in terms of x1, and I'm running out of space. So we're going to have x1 equals u p2 squared divided by 4p1 squared, all to the power of 1/3. Cool. So our Hicksian demand, guys, if we just isolate these, is our Hicksian demand for x1. So let's just write that. Our Hicksian demand for x1. Actually, let's make this different. Our Hicksian demand for x1 is going to be equal to u to the power of 1/3 over 4 to the power of 1/3. But 4 to the power of 1/3 is the same as 2 to the power of 2/3. And that we are multiplying by, in x1, p2 over p1 to the power of 2/3. So I've just simplified this one here a little bit, guys. And our Hicksian demand for x2, where is our x2? It is there, is going to be 2 to the 3rd u to the 3rd times p1 on p2, all to the power of 1/3. Cool. So finally what we're going to do is we're going to derive the expenditure function. So let's get to doing that. Okay, so finally, guys, what we're going to do is to get our expenditure function, part C, is we've got our original expenditure function up here, but the actual expenditure function that we're trying to minimize is actually the price of number 1 times the Hicksian demand for number 1, plus the price of number 2 plus times the Hicksian demand for number 2, which we find is equal to P1 times the Hicksian demand for 1, which is u to the 1/3 over 2 to the 2/3 times P2 on P1 to the 2/3 plus P2 times the Hicksian demand for 2, which is two to the 1/3 u to the 1/3 times P1 on P2 to the 1/3. Great. So now what happens is we're going to multiply into each of these brackets. So what we have is this P1 is like saying P1 to the power of 3/3. So when we multiply in, what's going to happen is this P1 3/3 and this is 2/3 in the bottom, so they will cancel effectively and it will just be 1/3 in the numerator of that fraction. So this is going to be equal to u to the power of 1/3 divided by 2 to the power of 2/3 times P1 to the 3rd, P2 to the 2/3 plus, and it's exactly the same with this one. That's 1/3, and up the top we have 1/3, and down the bottom we've got 1/3, so 3/3, so it'll be 2/3 in the top. So we've got 2 to the power of 1/3, u to the power of 1/3 times P1 to the 3rd plus, oh sorry, not plus, times P2 to the 2/3. Cool. So now what we're going to do is we could factorize it by P1 and P2 and u, and we'd have just 2 to the power of 2/3 plus 2 to the power of 1/3. And what that will actually give us in the end, guys, is we are going to get, just for the sake of space and time, 3u to the power of 1/3 over 4 to the power of 1/3, which is like 2 to the power of 2 on 3, multiplied by P1 to the 1/3, P2 to the 2/3. So what we basically have here, guys, this is our expenditure function based on our fixed utility. So that's what we're asking for, is it's what we're going to spend our money on is only based on our fixed utility and the prices of each good. That is going to depend what our expenditure is going to be. So to minimize our expenditure for any given price and fixed utility, this is how it will vary. So what we've basically done is we've taken the quantity of goods out of the equation because we've just optimized them and then subbed them into the expenditure function. So basically, guys, this is our Hicksian demand function here, and here's our, I'd almost call this a Hicksian expenditure function. But basically with Hicksian, we've got a fixed utility and we're trying to minimize how much we're spending to get there. I basically try and think about it like with Hicksian demand, it's like saying I want to get from, like fly from Australia to New Zealand. And I already know that I have to get from Australia to New Zealand. How cheaply can I get from one place to the next? That's Hicksian demand. For Marshallian demand functions, it's basically saying I have a certain amount of money in my bank. Where can I fly to? So rather than minimize your expenditure, what you've got is you've got a fixed expenditure and you maximize your utility for that expenditure. So I hope this video helped, guys. It was quite long-winded, but I hope it helped. There aren't that many videos that actually go through a problem like this from start to finish, so I thought I'd put one out there. But I guess with these sort of problems, you can get lost a bit in the actual algebra and stuff like that, so it's important just to keep trying to push through. But until next time, guys, just keep practicing and enjoy your economics and enjoy your maths.